In this video lecture, we're going to continue talking about the heat diffusion equation. Previously, we derived what's called the heat diffusion equation or the heat equation for Cartesian coordinates. So that consisted of considering a large solid, and we did an energy balance on one small chunk or node of that solid. So we took this little cube, assumed to be completely embedded within the solid, and then we computed an energy balance. We eventually shrunk the dimensions of our system, delta x, delta y, and delta z, down to be infinitesimally small or differentially small. And that created this partial differential equation known as the heat equation or the heat diffusion equation. So this is how it looks in Cartesian coordinates. We have our accumulation term here, generation term, and then these three terms each represent the in and out by conduction. And remember, because that's our little node, or this chunk is totally embedded within the solid, energy can only get in and out by conduction. So this equation also applies to other coordinate systems. So for example, in radial systems, specifically cylindrical coordinates, we would do something similar. We would assume that the solid chunk of material in this case is a cylinder, as you see here. And then the chunk, or the node that we take out of it, is this little chunk that's rounded on the inside and outside. So we would do something similar. We won't actually go through the derivation for this one here in this lecture, but you can see the derivation would happen similarly. You'd have energy flow by conduction in axially in the z direction. You would also have energy coming through it radially, so coming from the center and then leaving here. And then in terms of the angular component, we have this q sub phi going in this side and going out that side. So really, the derivation is very similar. It's just that the geometry gets a little bit different. And if you recall, because we pick up that angular term when we apply Fourier's law and are calculating the gradient, in this particular case, we also pick up some extra terms. So you notice some differences here. So we have this 1 over r outside of the derivative, and then we have another r inside of the derivative. Then this middle term, we pick up this d phi, and then we have 1 over r squared. These are things that would come out in doing the derivation, but you can see our axial term is pretty much the same as in Cartesian coordinates, because there's really no angles we have to deal with when we're going in this direction. So just important to note that in cylindrical coordinates, the heat equation looks different, and when we solve it, we do actually have to deal with these extra terms. But you'll see we're going to give lots of example problems where we'll work through these and figure out how to solve it in cylindrical coordinates for different scenarios. Spherical is similar, so we still have our accumulation term and our generation term, but now because we're dealing with two angles, the geometry gets even a little bit more complex. So here we have 1 over r squared appearing outside of that derivative, and then we have r squared appearing inside. And remember, those don't just magically cancel out. You have to go through this very carefully and systematically. Then the d phi term, dealing with the angle, this angle, looks like this. We pick up this sine squared of theta, and then we have the partial with respect to phi of k times dt d phi. And then finally, for the theta term, we have 1 over r squared times the sine of theta times the partial of this quantity with respect to theta. So these do look quite intimidating, and I don't think at any point during the semester we'll actually solve this equation with these terms. We'll typically deal with the one-dimensional form and just consider how temperature changes radially. And we'll find that if we can make that assumption that temperature only varies with respect to r, and that there are no variations with respect to the angle phi or the angle theta, then we'll find that this is a fairly simple equation to solve. Because if you notice, each of these forms of the heat equation, let's go back to Cartesian. So this is a second order with respect to our spatial coordinates, which means that for each spatial coordinate, we're going to have two boundary conditions. So what a boundary condition is, so when we derived this energy balance, if you recall, we considered that this little node was completely embedded within a bigger solid, so that only conduction is happening on the sides. Well, for the boundaries, there will be a node, or there will be some space that that goes up against a boundary. So something different will be happening here. So you could have something like convection happening, and that might be how energy is getting into this solid in the first place. Similarly, we'd have to consider this other side. Is energy also leaving this side by convection or radiation or some other means? So for each spatial dimension, this is a second order partial differential equation. So we need two boundary conditions for each side. So we need a boundary condition for the left side with respect to x and the right side with respect to x. We would need separate boundary conditions for the bottom with respect to z and the top with respect to z. And then finally, going in and out of the screen, we'd need two boundary conditions for y. And of course, if we simplify this and we're not thinking in 3 dimensions but only 1 dimension, then we'd only need the two boundary conditions. So if you notice, this equation, when we solve it, it's also going to tell us how a temperature evolves with time. So this accumulation term gives this equation a transient component. Transient means that it's not at steady state, but rather it changes with time. So that word transient just means how does this change with time. So if we're trying to consider how the temperature of something changes with time, we also need to know, well, what's the temperature distribution when you start your scenario or your simulation or when you start making some kind of change. So we will also need to have an initial condition. So we're going to need initial conditions. We're going to need to know what the temperature distribution is initially. So how does temperature vary with respect to spatial coordinate, and this is just for a one-dimensional system, and time at time equals 0. We would need to define some kind of temperature profile for however temperature varies with x and at time 0. So when we solve these problems, we'll need to make sure we have an initial condition and then two boundary conditions for each spatial coordinate that we're considering. There are different types of boundary conditions. So we could have that at one boundary we just know a constant surface temperature. We'll just assume that the temperature at x equals 0, considering just the x dimension, and at time t is always going to be this constant surface temperature. So back to our example, we could just assume that this side is fixed. So we don't really need to know if it's coming in by convection or radiation or conduction. We just need to know that that temperature is fixed, and that knowing that that temperature is fixed would allow us to define a conduction term coming in. So that's the fixed or a constant surface temperature boundary condition. We could also have a constant applied heat flux. So we could assume that even if we don't know what's happening on this side, we could assume that there is just a constant heat flux the entire time. And so that would allow us to define what the derivative is. So this is essentially a surface energy balance on that left side, and we're just saying that this constant heat flux that's coming in is going to be the same as the heat leaving that surface, that control surface, by conduction. So we're just saying the heat coming in is just a constant. It doesn't even really matter how it's getting in. We just know that it's a fixed mathematical constant. And then leaving this surface, if our control surface is infinitesimally thin, we know that energy could only be leaving this solid, going deeper into the solid by conduction. And so we would just apply Fourier's law there and say that the conductive heat flux is minus k times the partial of t with respect to x. And finally, it could be coming in by convection, so we could have an ambient temperature defined and a heat transfer, convective heat transfer coefficient. So in that case, we would just say energy, again, this is a control surface energy balance. So energy would be getting in by convection, and it would be getting out of this infinitesimally thin control surface by conduction. So that's all we're saying, is it's going out by conduction, and we equate that to what is coming in by convection. So depending on the different boundary conditions, we may have different math to deal with when we're solving the heat equation. Finally, and I should have said this one earlier, a special case of this constant heat flux is zero heat flux, with a surface being perfectly insulated, where we would say that the derivative of temperature with respect to x is equal to 0. This is also similar to here. If we know that this constant surface flux is 0, we could just divide both sides of this equation by k, or by minus k actually, and we would end up just, the k doesn't matter, and we'd end up with something like this. So you could have that there's no energy coming in because the surface is insulated. And what that does is it just tells us that the derivative of temperature with respect to 0 at that particular location is just 0. And you can see that here. The temperature derivative is flat here. And then for whatever reason, it would be curving later on because there would actually be heat, or there could actually be heat flow later on. Perhaps if the solid generates in some way. So this may be a little bit esoteric to you right now, but I promise you we'll solve some example problems, and you'll have homework problems where you'll be reducing the heat equation to simplify it, and you'll be applying different boundary conditions and solving. And despite the fact that those PDEs can look quite ugly and gnarly, we're going to trim them down and greatly simplify them so that we can solve them using fairly simple integration techniques. Okay, so let's actually look at some examples. How would we reduce the heat equation using some simplifying assumptions? So let's look. So I'm going to read this thought problem, and then I want you to stop and think about what the answer is. So you can hit pause or something while you think about it, and then I'll give the answer. So a long concrete cylinder is heated by an electrical wire running axially down its center at r equals 0, but only on one end. How many dimensions, or how many spatial coordinate variables, should we use to represent this system? So let me describe this problem. So we're going to have a z component here. We could define z going from left to right. We could define it going from right to left. As long as we stay consistent in our definitions, it won't really matter. So then we'd also have a radial component here, r, going from the center outward. And we could also have that angular component, phi. So this version of the heat equation, so I skipped a step. I've already given you the heat equation in cylindrical coordinates, and we just need to think through which of these terms can we get rid of and which can we keep. So I do want to point out the drawing's not perfect. So this is a heated wire that's just on this right end. And although so this is going to be at the very center radially, so it's actually would be in the center, but it doesn't make it down this far all the way to the left. It's only on this right-hand side. So at this point, I'm going to invite you to pause and think about this. How many dimensions do you need, and which terms can you eliminate? Okay, so let's think about this. The way I would think about this is, how would I expect temperature to change? So I have this side being heated, so I expect this right side to get hotter than the left side because the left side is not being heated. So I would expect it to be hotter here in terms of z and cooler here. I would also expect, because this heat is at the center, I would expect it to be hotter right at the center at r equals 0 and less hot out on these outer edges. So that tells me, if it's going to it being hotter on the right side, it tells me I'm going to need this axial term because I'm expecting to have temperature gradients. This dt dz will be non-zero because we're expecting it to be hotter on the right than on the left. Similarly, I'm going to expect it to be hotter in the center than on the edges, so I'll expect there to be a measurable temperature gradient in the r direction. So this term is going to be non-zero. So I'm going to have to keep that term. So we'll need to keep those terms. Okay, how about this term? Do we expect any angular variation? So with respect to phi, if we're going angularly from here to here, do we expect there to be any temperature variation? The answer there is no. This is a symmetrical system, so it's symmetrical about this inner radius. So we wouldn't expect there to be any changes going in this angular direction. So this term we can get rid of, and we can justify that by saying as you go around this angle, you don't expect there to be any change in temperature. So we can actually nix this term and just treat it as 0 because that temperature with respect to phi is 0. Now the question doesn't actually ask this, but do you see anything about generation? So this is actually kind of a tricky question. So we would potentially have a generation term depending on how we're treating that wire. We could treat it as having no dimension and it's just almost an in term, or we could treat it as having some kind of space. But so that's probably more than we need to worry about right now. We're also not told anything about whether it's steady state or not, so we probably should keep these terms. But really, the question just asks, in terms of dimensions, we need to keep the axial and the radial components, but we do not need to keep this angular component. All right, let's look at another problem, a spherical one. A hot metal sphere at a uniform initial temperature of T0 equals 500 Kelvin is dropped into a tank of cooler quench oil at uniform constant temperature of 280 Kelvin at T equals 0 seconds. There's our initial condition here. And then we're also assuming this is going to play into our boundary condition, except this will be a convection boundary condition because it's the fluid that has that constant temperature. So at time equals 30 seconds, I would like to determine the temperature distribution in the sphere. How many dimensions should be used to model the system? So we're assuming that the sphere is just sort of hanging in the air somehow. Maybe it's suspended somehow. So that should play into our thinking. All right, so I'm going to pause, and I want you to think, how many spatial dimensions do we need to model the system? Okay, I hope you put some good thought into that. So remember, in spherical coordinates, we are going to have a radial term, r, and then we're going to have an angular term. So this could be phi in this direction, and then theta would be coming in and out of your screen at an angle. So would we expect there to be any angular temperature variation? The answer there is no. This is also, there's some symmetry here, again, because of the radial nature of this system. So we'd have symmetry, but it's going to be in both of those directions with respect to theta and with respect to phi. So that means we would not expect any temperature gradients with respect to those angles, and we could just eliminate those two terms entirely. This problem, we're not told anything about generations. We can get rid of the generation term. However, this is definitely a transient problem, which means temperature is changing with time. Because we've dropped the sphere, it's initially at 500, we're going to drop it into this fluid at 280, and we're going to expect it to be cooling over time. So we'll definitely need to consider this term. Also, as the cooling, I guess, penetrates in, so we're going to have heat leaving this by convection. So we're going to have this QR term. So we'd expect the outer layers of the sphere to cool before the inner layers of it do. So we would expect temperature gradients in the R direction. But as you can see, we got rid of some of those complex, ugly terms and are left with a much simpler form of the heat equation to solve. All right, let's look at the plane wall. We've sort of talked about a plane wall. So a plane wall system is, you can think of this as when you have a really large wall and you're expecting things to be somewhat uniform. So if this is the wall inside your house and you have this ambient temperature inside your house, and maybe this is outside, let's just call that T out. Let's call that T out and T in. So you might expect convection. You'd expect this air to be circulating reasonably well with the ventilation in your house and just natural buoyancy effects. Similarly for outside. So you'd expect everything outside to be happening fairly uniformly and everything inside to be happening fairly uniformly. So that means if this is a larger wall, what's happening in the Y direction or in the Z direction, we can assume that those would be fairly uniform in those directions. However, if it's really hot outside, since it's August as I'm recording this lecture, let's say it's 100 degrees Fahrenheit outside, and inside, let's say we're cooling our house down to 70 degrees Fahrenheit, we would certainly expect temperature variations in the X direction. So we'd expect, if we plotted temperature, we'd expect to see the temperature increase as a function of X as you go deeper and deeper, and certainly by the time you got outside, you'd have a much higher temperature on the outer surface than you do on the inner surface. Okay, so let's look at how that applies to the plane wall system. And I'm going to ask, this wasn't one of my thought problems, but I'm going to ask you to pause and think about which terms can you get rid of in the heat equation. Okay, so hopefully you're getting more comfortable with doing this now. So we're not expecting, because of just conceptually, we expect convection to be happening fairly uniformly on the outside and the inside. We wouldn't necessarily expect there to be any major temperature gradients in the y direction as you're going down the width of the wall, or in the z direction as you're looking at the height of the wall. So we can get rid of those terms. And since I talked about this being your home, you probably don't have heated walls. So a generation term is something we wouldn't have to worry about. So this actually is the definition of a plane wall. It's a one-dimensional conduction problem within a planar medium with constant properties. So that means our K is constant and not a function of temperature or distance. And it also has no generation. We can simplify this even further by assuming that our system is at steady state. So if at steady state, then we can eliminate this term. And then we just get this equation, d by dx of this quantity k dt dx equals 0. And if we keep the accumulation term on there, I'll come back to the steady state version of this. It looks like that, so easier to solve. We can also just make some rearrangements. If we can pull k out because it has constant properties, so if k is constant, we can pull this out of the equation, out of this derivative, and then we can divide both sides through by k, and then we can replace that whole thing. We can define k, this happens here on the slide. So alpha is defined as k over rho times Cp. That definition is called the thermal diffusivity of our system. So just another way of sort of lumping constants together. So the combination of density, heat capacity, and thermal conductivity of a solid tells you a lot about how fast things are going to happen, how fast temperature is going to penetrate into a particular solid. So this equation can also be greatly simplified because we're just considering one dimension, and if we're not considering time, so let's take, if we have d by dx of k times dt dx equals 0, because it's just at steady state, well, we can actually, again, if k is constant and not a function of temperature or a function of x, as I mentioned before, we can pull that out. We no longer need to use the partials actually here, so we actually get an equation that looks like this. K times the second derivative of temperature with respect to dx squared is equal to 0. So when we have a plane wall, which is a one-dimensional problem with constant properties, constant thermal conductivity in particular, no generation, and it's at steady state, we get this form of the equation. So what does that tell us? And actually, you can divide both sides through by k, and you just find out that the second derivative of temperature with respect to x is 0 under those particular circumstances. So that tells us if the second derivative is 0, it tells us that we have a constant slope. If we have a constant slope, that means our temperature profile is just a straight line. So breaking down the heat equation is where we get to this result that temperature changes linearly as a function of x when you're only considering one dimension, i.e. it's a planar medium, has constant thermal conductivity, no generation, and it's at steady state. So we'll cover that later, especially in chapter 3. We'll be solving kind of problems using this, and stay tuned for the next video where I will do an example problem to figure out what's the temperature profile in a plane wall.